Howdy! Chapter 9, the magnetic field. You have now seen that we have the laws necessary to accurately predict what will happen when we connect batteries to resistors and capacitors, at least in the steady state. You should remember that we started with Coulomb's law, which described the force that one charged particle exerted on another. From this force, we define the electric field vector, and this E is at the heart of any calculations we have done. Now we consider a number of experimental results which clearly show that there is another force acting on charged particles besides F equals QE. Instead of starting with the force, the magnetic force, and defining a magnetic field, we are going to start with the field. The reason for doing this is the rather complicated vector nature of the magnetic force. We will find that the relationship between the magnetic field and the force on a charged particle involves a cross product, and that the relationship between the source of the field and the field itself involves another cross product. To avoid starting with a double cross product, we first consider the effects of the field in this chapter and tackle the production of the field by its source in the next chapter. It would be nice to show you a video of charged particles experiencing a force due to the presence of a magnetic field. This is easier said than done. You have to believe the results described in the book, which are best explained by postulating the existence of a strange field. In terms of the magnetic field, B, the magnetic force is found to be F equals Q V cross B. The units of B are sometimes called Tesla, sometimes called Gauss, and sometimes Webers per square meter, depending on the context. It is shown how this strange cross-product force leads to the experimental results for charged particle motion. This will give you a chance to revisit some entertaining Physics 218. Magnetic fields have many useful applications, one of which is the velocity selector, critical in some medical treatments. It involves both electric and magnetic forces. Finally, the force that is exerted on a current-carrying wire by a magnetic field is calculated starting with the force on a single particle. Here is where we need the drift velocity that was calculated in the previous chapter. This result is much easier to demonstrate than those involving single particles. The result is that for a wire of length L carrying a current I, the magnetic force is F equals I L cross B, where the direction of the vector L is defined to be in the direction of the current. Just want to demonstrate a magnetic effect. It would be nice if we had a charged particle Q that was moving with a velocity V in a magnetic field B, and you could see the magnetic force given by the cross product. Unfortunately, I don't have a supply of moving charged particles except in a wire. We know that in a wire, the force on a small piece will be the current, the tiny length, crossed into the B field. So what we have here is a permanent magnet. The B field points from north down to south. I will connect a battery so that we will have a current. The current flowing from the plus to the minus. So the current is going to be going in this direction. The B field is down. So if I connect it as is, this wire should feel a force towards me. If I reverse it, then the current is now in this direction. The force should be out. There we have a demonstration of magnetic effects. One of the problems in the book has to do with the torque on a current-carrying wire in a magnetic field, and this will turn out to be quite important for engineers. Summary. It is shown that certain experimental results are described by postulating the existence of a magnetic field B. The magnetic force due to this field is given by F equals Q V cross B. A current-carrying wire of length L in a magnetic field experiences a force given by F equals I L cross B. The source of B is the topic of the next chapter. Gig 'em!